All right, good afternoon or good morning, everyone. I'm Luis Huerta. Um, I I am volunteering to help out Lou and Tammy in running meetings. So I'm not chairing or co-chairing. I'm just being a good helper for them. So today our speaker is Mark Eggler. Mark has over 25 years experience working on complex projects as a senior professional engineer and program manager. He has niche expertise in technical definitions, systems engineering, and program management of complex military programs. And over the years, he has worked on many of large-scale military acquisition programs in the US, Australia, and the Middle East. In 2000, Mark was awarded a Chief of Army Commendation for outstanding achievement in programs and engineering management. In recent years, Mark has focused on developing a market-leading technical institute of technology. He has designed and developed a broad range of niche technology training course specializing in capability system design, system engineering, military vehicle technology, project management, leadership. He now delivers these professional development courses in governments and defense companies around the world. He graduated from RMC Dutron in Australia with an honors degree in mechanical engineering. He holds a Master of Science in Defense Technology and has completed a broad range of postgraduate studies in economics and finance. Mark is currently visiting a fellow at the University of New South Wales in Canberra. So everyone, welcome Mark Eggler. Today he'll be talking about using model-based system engineering techniques to support requirements generation for the design of new generation of armored combat vehicle systems. All right, take it away, Mark.
Thank you, Lewis. Good day, everyone, and it's a pleasure to be with you today. So I'm just going to share my screen with you now. So throughout the presentation, it'll run for about 45 minutes. There'll be segments where I talk to presentations just to introduce the topic, but most of the time we're going to be in the demo tool, and I'll be demonstrating how we can actually use systems engineering and model-based systems engineering to develop our defensible and logical requirements set. So we're going to follow the design essentially of a new generation combat vehicle system, just to put some context around it. I'm sure you'll find it quite interesting what I'm going to cover. So, right, so just let me now share my screen. Okay, so this is what we're going to cover over the next 45 minutes or so. So let's go. Righto, so thanks, Lewis, for the introduction. Okay, so let's just put everything in context here. Modern engineering today is highly complex. And as you can see, we're living in this world now where we have this great interconnection between all the elements within the system, or even those elements that are external to the system itself. The thing I'd like to just say is that we're at the point now where even low and moderate complexity projects can have many hundreds of requirements, if not more. And given that, it's just simply not possible for the human brain to be able to manage all those requirements in your head. And therefore, we do need to move into an environment where we've got tools to assist us with that. So obviously, we're now moving into the age where we've got model-based systems engineering and great tools that can help us to manage this complexity and this vast array of information that gets related within the design of complex systems, and particularly the requirement set. So as you know, we started off with drawing boards 30, 40 years ago. I certainly did. And then we moved into 3D CAD drawings. Nobody does that. So the idea is that we now, on the right of the screen, you can see that we basically move from our document-centric view of the world into using tools. And it turns out that they've got a whole range of great benefits. And I'll touch on some of those. So MBSE, there's the definition. I'm not going to go into great detail, but put it simply, basically it's systems engineering. We're using tools, a tool to help us move through that process from basically identifying the user's needs through to realization of a physical system. But the interesting thing is that when you actually do your modeling in tools, you move away from this linear based approach, which you've essentially got when you're using document-based artifacts to move you through the design process, into the ability to actually see things much more holistically. And we obviously have the great advantage that we can develop and create great traceability between the elements within the model as we're actually doing our design. So where do requirements come from? This is a common question I get from people and students when I'm teaching them. So I just wanted to show briefly on this slide that there are actually 5 ways we can generate requirements. We can generate them from our constraints, which comes from the operational domain. We can also generate qualities and characteristics, which generally come from the operational domain as well. Get our requirements such as our reliability and maintainability and things like that, things that end in ilities. Within the system domain, we've got our functions that drive requirements, and then we have our components and interfaces that also drive requirements. So we've got this model here that nicely explains the 5 ways that we can generate our requirements as part of our system design. And in the demos that I'll do shortly, you'll see a number of requirements generated from functions and interfaces. Okay, just simply don't have time to sort of step through the process for the whole 5 generating areas. So we'll be using a tool. It's a simple tool. This particular tool, as you will see, is very good at doing what I call the top half of the systems engineering V, particularly where those people, if those people are working in government, its strength isn't in the bottom part of the systems engineering V, but it is good for teaching. So it's a great way to sort of look into the actual sort of systems engineering process and learning how the thinking is different, right? So that's the tool. We'll be using a simple tool to demonstrate how we generate requirements. Okay, so we're going to start at the front of the process, operational analysis. You'll all be aware of the systems engineering V. Operational analysis occurs in the top left-hand corner. It's all about identifying a set of user needs. And it's obviously, it's a really important part of the process. In my view, the operational concept document that emerges from this particular part of the process, I consider to be the capstone document of the whole system design process. If you don't get this right, we know from all the history and the studies that have been done, you're likely to end up in a world of hurt. Now, to do this, to generate the operational concept document and to organize all that data, we basically need to be able to transform all those things that are going on within the operational analysis process. And I like to use what's called a capability design information architecture, just to help think about how all this hangs together. So here you can see that we've got a simple model that connects together the performers who are performing the operational activities. The performers are connected together or interface together and create what are called operational connections. And the operational items are transferred across the operational connections. And basically our operational items are inputs and outputs of operational activities. So that's the basic model that I use when I'm doing my operational analysis to get at the operational needs. So to get at the needs themselves, we need to generate scenarios and vignettes. Basically, these operational activity diagrams. You'll be familiar with these operational views as part of the DODAF process. These are very useful because they give us the ability to see things temporally, what's going on, and then we have a clear basis and understanding of who's doing those operational activities and what operational needs emerge from each of those operational activities. And again, you'll see that in the modelling process very clearly. We can then put these into another operational view, OV5, and basically you'll see here the operational activities put into swim lanes, and where you can actually see what performers are doing what activities. And we can also have those operational items, which you'll see in green there, basically being outputs and inputs from various activities. And then you can see with the blue lines that basically we can use those activities to drive out the operational needs. So this particular way of approaching operational analysis is very systematic and certainly minimises the chances of gaps when you're going through this part of the crucial front end of the systems engineering process. Once we've got our set of needs, we need to shape those into groups, and we can emerge what's called the operational needs hierarchy. Okay, so that brings us to the first demonstration. So just let me bring up the model. Okay, so here we've got the model that we'll be doing the demonstrations with. On the left here, you will see the classes.
Hey, Mark.
Yeah.
We had a question of what tool is this capability architect?
Can I address that information at the end of the presentation?
No, sure.
Yeah,
I'll compile the questions for you then.
Yep. Okay. So we can just hold the questions to the end, and then we'll have a nice session when I finish everything. Okay. So we have this tool running down. We have the operational classes, and within those, so let me just start here because we're dealing with performers initially. So we can basically create these nodes within the model, and when we click on that, we activate the main screen, and here you'll see a description screen. We can create metadata in it. Down here is a pane where you see the cursor, where we can actually connect our information as we're doing our analysis. And that basically creates our nice traceability. And if we actually link to a particular node in the operational activity part of the model, we can actually see what that actual operational activity is that we've created. Okay, so the first thing we're going to do now is we're going to create a performer, right? So when we start the process of designing any combat vehicle system, we need to understand who's doing what. Okay, so we're going to create a performer. We can see here we have an amphibious task group, and within that there are some organisations, and within that I'm going to create an enemy element within that, because they're a part of the overall actors in the design process. So we're just basically going to create a node, and we're going to add in that element, the enemy force, which is really important. Okay, and now that's been added in, and we're going to add in a short description. Okay. And then we can select a performer type if we think that's appropriate. We're going to add in another performer as part of the mechanized battalion group. Okay, so we just add a node into that. We're going to add in the battalion commanding officer. Okay, and we're going to do the same thing. We're going to put a short description in to the model as we're going. Now, remember, as we're doing the modeling process, it's absolutely essential that you put in detailed information into the description system. If you don't, you just end up with an empty model, and it really isn't very helpful to anyone. And when it comes to generating our document, the information comes out of the description section. Okay, and we can now create a link to, as part of this, to say that the battalion CO basically is part of an organisation, and we're going to say he's part of Land Force Headquarters. So we just double click on Land Force Headquarters, and you'll see here that we've now created the trace showing that this particular stakeholder, the battalion commanding officer, is part of the Land Force Headquarters organisation, which is really neat. We can move him up and down within the model if we want, because he's important. We'll put him at the top of the tree. Okay, so he's now up there at the top of the tree. Okay, so we've now created a performer, which is the first thing we need to do, because our operational activities get performed by our performers. So now let's just collapse this part. We're now going to look at operational activities. Okay, so within that, we need to create a series of scenarios in vignettes, which I've already done here. You can see in the model for this particular system. We're going to look at an amphibious landing, and we can see here that there are a whole lot of activities already created. And I'm going to add into this amphibious landing a new operational activity called secure the beachhead. So we'll add a node. And I'm just going to put that in now. Oopsie. There we go. Secure the beachhead. And we're going to add into this particular node the description. Okay, so there is a nice description which is explaining exactly what's going on within that operational activity. And you can see down here, we've got a range of metadata that needs to be completed. So down here, because we're designing a vehicle system, we need to put in how long the vehicle is off. So let's say it's off for 60 minutes. It's idling for 30 minutes, say, as part of this task. It's communicating for 5 minutes. It's using its surveillance target acquisition systems for, say, 3 minutes. It's using its night vision equipment for, say, 3 minutes. And it's firing some weapon rounds, let's say 200 rounds of weapons, and it's driving on roads and tracks in a certain amount of time, let's say, certain distance. And the total duration of this particular task, we'll say, is 120 minutes. So we've now entered in all our metadata as part of that operational activity. This is absolutely essential, so we get an understanding of what's going on within each of the key systems within the vehicle at this particular point. And the other thing is that it greatly assists the reliability engineers in easing out the reliability metrics. Okay, so this particular task, secure the beachhead, we'll now move that up to its correct position. So it's now here at this particular point in the activities. We need to identify who is actually performing this. So we go down to performed by our company OC, our company officer commanding. We double click that. We can now see that we've created that trace from the performer to the operational activity. And then we can go and have a look at our operational activity diagram to confirm from a temporal perspective what is going on. So you can see here, we've now got our nice operational activity. We can see that how the actual activity is being occurred. We've got these various elements. We can see here that secure the beachhead is not in the correct position. So we can now just come and move that to the right position. And of course, as we're doing our modeling, if we're in a workshop, we can talk to the key stakeholders, and they can then point out and say, no, let's move these things around. They're not quite correct. We need to basically have this particular temporal flow. Okay, so that's really nice when we're doing it, the operational modelling process. It's quite easy to just continue to add in additional activities as you go through the process with the user and the key stakeholders. Okay, now just let me see if there's a few other things we need to add in here. Okay, so we've basically created a simple operational activity model there. Now, once we've done that, we've got our first cut of operational activities. We're now able to go and generate from these activities our operational needs. So I'm now going to open up the operational needs class. And we can see we've got our consolidated operational needs set. I've already done some work here. I've created a hierarchy already. And I'm now going to add in a protection related need in this particular model. It's because we've looked at an operational activity relating to one of the activities. And we're going to see that, oh, we actually need to be able to navigate the vehicle whilst in a closed down condition. So we're just going to add in this particular node into the model now, navigate while closed down. We, of course, need to put our description into our model, exactly what's going on. You can see there providing information about what the crew commander needs to know. And of course, we need to link this need back to its actual operational activity. So this operational need is the result of an operational activity called advanced contact 115. So I've just got to find 115. There it is, advanced contact. We click that and we've now created the link. So we can see that we're building up a picture here where we've got the operational need connected to the operational activity, and the operational activity is linked to the performer, so we know exactly who is doing that. Of course, we can move this around if we need to in the model, put it in its correct position in the tree. And of course, at this particular point, we can now also generate the actual operational needs hierarchy straight out of the model if we want to, which is really nice because I like to look at things in tree diagram format. And we just develop that. And of course, we can look at the different levels that we might want to do. As we develop these particular views, we open them, they automatically save an image of that within the model. And then if you've created a OCD template, for instance, you can then automatically generate these particular images into the actual document, which is fantastic because, of course, you know that nothing's static. As we're changing and developing different parts of the model, we don't have to, we don't want to be having to save diagrams and then paste them into documents, right? So when we're in the model environment, this just nicely does that for us. Okay, so that's basically finishes off the operational part of the demonstration operational analysis part. Of course, we could and would, if we're continuing the analysis, develop our operational items. We don't have time to do that this afternoon, but we would obviously then do that, link those operational items. We would create links where the performers are connected together and identify where those operational items pass, what activities they're passing into and out of. So, okay, so that brings us to the end of that. So let's just now go back to the next part of the analysis, which is dealing with our functional analysis, right? So as we come down our systems engineering V, we get into the functional analysis part of the design process. And this is where we're basically transforming the operational needs into a functional architecture. We're deriving the functions of the system. We're organizing those and creating our functional flow block diagrams. And as we're generating functions, we are generating our system requirements. So this is obviously a critical part of the process because we're now moving into the system domain. And we're using the model and this logical process to generate quite clearly and logically and defensibly where our requirements come from. Right? So I know that throughout my career, I used to go to things called requirements workshops, and people would just be sticking their hands up in the air and saying, okay, we're now going to get our requirements from people's views on what the system needs to do. That's not a good idea. It should be done logically through the operational analysis process, and every function that emerges in the analysis process should be traced straight back to an operational need. If it can't be, then it's basically an orphan requirement and what I call forming part of the gold plating of the system. So if we use this logical process, you will have everything will be defensible. So onto the left of the screen, you'll see the operational domain. And on the right, you're going to see the system domain. And basically, we're now going to use our operational needs to be the basis of our functions. And once we've created some functions, we can then start specifying system requirements. When they're all amalgamated, they end up in our function and performance specification, or PSpec. We create a consolidated FFBD, which is basically the high-level functional Flowbot diagram for the system. And of course, in the model, we can double tap each of those high-level functions to drill down and see the lower levels of what's going on. We can also generate our consolidated functional hierarchy. And again, using the tool, we can easily drill into that and put it in different formats. Okay, so basically this is the modeling schema that I'll be demonstrating to you shortly. I'll be showing you how we generate our functions from our operational needs, and then we're going to generate our system requirements. We'll talk about the other elements in the model when we get into the physical design part of the presentation, which is coming up next. Right, so let's cut back to our model. Okay, so what we're going to do first is create a function. So we can see here that we've got within our model an operate the IFV system, operate the infantry fighting vehicle system at the highest level. And under the maneuver node, so at this particular level 1 in the tree, we're going to develop and insert a new node. Now, I would also just say in passing that these functions at level 1 within the model are generally what I refer to as the mission essential functions. I'm not going to go into that in any more detail now, but those at the high levels within the tree are the most important. Okay, so let's add a new function into here, because we've done our operational analysis. We've identified an operational need, has driven the need for a function called climb gradients. Okay, so we're going to add this into our model. Climb gradients. We're of course now going to put in the functional description, and in this case, I've put it in terms of a system requirement, but it doesn't have to be at this particular point. It can just be a general functional description of what that function is, because we're going to generate the actual requirement a little bit later. Of course, we need to link it back to what is the operational need. So we come down into the classes pane down here, and we find this area here. It's based on operational need called incline acceleration at 132. So we just find that particular item here in the model, 132. We link that together, and now we've got a nice trace from the operational need to this function. In this early stage of the modelling process, it's also good practice to link the function to its component, because functions, as you will know, are allocated to components. So we haven't done the actual detailed physical design yet and identified subsystems. So we would just start by allocating it at the actual black box level, which is the infantry fighting vehicle system. So I've just got to find that within the tree here at 1.1.1. Where is it? I've got a lot of stuff in here. Just let me try and find the correct one. There it is. Okay, so we've now got this particular function being performed by the component. As we'd process through this design, the design process, we would then reallocate this function from the black box onto the actual subsystem or lower. Okay, so we've now created a function, and you'll recall from my little model that we use functions to generate system requirements. So we come down here, we can see that we've created a series of system requirements, and we're now going to add in a system requirement from this function. Under maneuverability, again, we add a node, okay, called gradients. And we put the actual system requirement into the description section. So there it is. We've got a series of metadata fields here that we want to fill out as we're going through. What priority is it? What is its verification status? So it's open. What's the verification method? The systems engineer may do this, or it may be the test engineer's responsibility to do this. So let's say we're going to do it by demonstration. Is it a key performance parameter? Is it a load case? What's its origin? If you're working in industry and it's come across from government, you'd put it as the original. If you're working in industry and you're doing this, you might say it's a derived requirement from something else. You just select what that is. Select the requirement type. It's a performance one, function of performance. Is it allocated to a verification package and skill set? So these are sort of T&E things, which are verification and validation issues, which we won't cover off today. Okay, so we've now, as you can see, we've created our function, we've created our requirement, but we've got to link our requirement here back to the actual function. So it specifies a function, and we just need to link that back to, just let me check which one it is. It's here, it's 117. So let's go and find 117 in the tree. 117. Okay, and we just add that in. I think I saw it there. There it is. Okay, so we've now basically created the nice traceability from the requirement back to the function. Again, good practice to make sure that you're actually doing the traceability as you go. Don't create your functions and your requirements without creating the traces. It can be difficult to locate them later on, and you may lose your the actual clear lines of thought as to why or which functions they are traced to. So do it as you go. That's best practice. Okay, so what we want to do now is we've created a series of functions. We can now go and have a look at our functional flow block diagram. We can generate that, and here we can see that we've automatically generate our FFBD from the model, which is very nice. If we've created any items that are moving, have been identified in the operational analysis part of the thing, work that we've been doing. These would also appear here if you've created the actual interfaces, so we can show data items on here. So at this point, we would have been creating physical interfaces as well to move these actual items within the physical system itself. So we can see here we've got some target information moving from the sense function into the destroy function related to the weapon system itself. Okay, so that brings us to the end of the functional analysis piece. Of course, again, there is plenty more that we could talk about, but we're time limited today. So just let me collapse the model up. And let me return to the presentation. So we're now going to move into the last part of our session today, which is looking at system design and synthesis. So we're now at the bottom of our systems engineering V. We've completed our operational analysis. We've now derived a functional architecture and a series of system requirements, all nicely linked and traced together. And we're now going to cut across that into the actual physical domain. So the aim of what we want to do now is to transform our functional architecture into a first cut physical architecture. And as we're doing that and generating physical elements and physical interfaces, we will also be generating system requirements related to that part of the design work. So we can see here now we come back to our schema, which is linking all of our information together within our model. We've now added in from our functions, we've now got components. We're going to build our model, build our system based on a series of components. Those components are connected together by what we call links, and they obviously create interfaces. And items are passed over those interfaces, be it electrical signals or hydraulic pressure or hydraulic fluid. And the actual items are inputs and outputs of functions within the system. So the important thing to note here is that as we generate components, they will generate requirements. So we're going to generate system requirements. And also our interfaces, right, that we create will also generate a series of system requirements. So we've now got within the physical domain, we've got requirements coming from functions, components, and links as shown at A, B, and C. Okay. Once we've done all that, we can then use our model and our templates that interface with our model to automatically generate those additional documents shown on the screen. From this, we can generate our product breakdown structure in hierarchical form, nice and easily from our model to view what we've built, what we're designing. And of course, we can generate our interface diagrams, which again is very nice. And as we update things, we automatically create our new images, and then they can automatically be updated in our actual physical Word documents or whatever we're using. So we need to allocate our functions onto our physical system. So you would have seen before that we started by allocating at the black box level. Well, now as we're digging down and we're actually creating the physical architecture, we're now going to allocate our functions at the leaf level down onto the subsystems initially. And we do that because that enables us to create our subsystem specifications nice and easily again from the model. Everything connected together, everything is, the requirements that emerge are all defensible because they're linked back together. We can actually trace them right from the component back to the actual operational activity and the performer, which is really neat because if we need to justify any part of the model, or we want to excise something from the model, we can quickly identify the impacts. So there's the overall schema. It's in these slides. I'm not going to run through this now, but it's there for your future reference if you want to come back and have a look at it. So, right, so let's just move into the last part of the demonstration where we move into the design and synthesis part of the systems engineering process. So we're now going to create a component. So we go into our components part, components class within our model. And the first element we're going to create, first component, is an external component. And we're going to add in a aircraft type. So again, we just add a node, right? And just let me use the correct code here. So we're adding in a external system that the combat vehicle needs to interface with. It's an A400M aircraft. And of course, we're going to add in the description of that. Okay, short description there. Is it a CI? We can tick those if we want them to appear in our system description document. Is it subject to any sort of form of configuration control? And we need to add in our metadata, which is important. So we know who the manufacturers and product numbers are. So we can just add those in. Its product number. And is it a make or buy decision, which is really important. Okay, so we're just going to, obviously, we're not making it because we're designing a combat vehicle. So this would be government furnished material or GFM. And we can allocate what component type it is. Is it a system, subsystem, whatever? So that could be added in if as needed. Okay, now what we need to do is, now that we've created this, we can move it up and down in the tree if we want to. But shortly what I'm going to do is I'm going to create an interface where I will link this actual component to, because it's external to the model. And we can also generate and have a look at our overall system level hierarchy at this particular point if we wanted to. So we can again show the hierarchy, and we can see quickly basically what is within the system. So we're one level down. So just let me go up one level. So we've got the correct view here. Hierarchy again. We can now see that at the system level, we've got our armoured fighting family of vehicles, and then we've got these external systems that we need to interface with. So now let's create an internal component within our system. So this is what we're actually designing. So let us go to the infantry fighting vehicle system that is subject to our design work. And we're now going to add in the engine subsystem to the model. So let's just add in our engine subsystem. Okay. No, let me put in the right one again. Just check that. I put the wrong. Here we go. Here's the better one. That'll get us the right one. Here's our engine subsystem. Of course, we add in our description. Okay, so there it is, describing where the engine is supplied by, and it's some of it just its general technical characteristics and parameters. And of course, we can add in the metadata. This one is going to be a configuration item, so we tick it. We add in who the manufacturer is and the product number. Okay. And for this particular one, we're going to buy that. We're not going to make it. So obviously, very important part of the technical management process is to identify whether we're making or buying it, because that will drive the amount of work within the overall program. Okay. Now, what we need to do is, again, this would be linked. This would have functions coming onto it at some point. So I'm not going to link any of those now, but you would see here we'd come down to perform functions, and we would go through those and identify which particular functions are performed by the engine subsystem. So we would allocate those at this part of the process as well. So I'm now going to create an external interface just to show you how that works. So what we need to do is under the link class here, we're going to create an external interface. Okay, and we're going to create an interface between the A400M aircraft and the infantry fighting vehicle system. So just let me add that in. Okay, so there it is. So that's the interface. Just let me check the, it should actually, just let me add that in, it should say IFV there. So we know that it's an interface between the IFV and the A400M aircraft. We add in our description, okay, which is obviously important. And we click what the interface type is there. We select the interface, and we can also describe what type of link type it is. And for this one, it's a mechanical interface. Okay, so we've now created our external interface. The only thing is that this one here needs to connect to something. So what we're going to do, just let me move it to its correct place in the model. So this external interface connects two components. So let's connect the two components that create the interface. Okay, so the first one is the A400M aircraft. So there's that one. And it also connects the IFV system. The reason the numbers are the same is because the tree hasn't been refreshed. So if I refresh the trees, they'd be allocated the correct numbers. So, okay, and what we can now do is, if we want to have a look at the interfaces that we've created within our model, we can go back to our components, and we can show our interfaces that we've created. So, and here we've got a nice view of our interface, one of our interface diagrams. You can see there that the external systems are shown in white, and the internal or peer systems are shown as the same color here, right? So that's a high-level interface diagram showing the IFV system interfacing to its external and peer systems. Okay, the last thing is to just show how we would generate a requirement now in relation to that interface that we've created here, this one here, our external interface between the infantry fighting vehicle and the A400M aircraft. So we go back to our system requirement, and under interfaces, we're going to create an external interface requirement. Okay, so let's just create our heading node here for all those requirements relating to that particular interface. Okay, so we've got that there. We'll add another node because we're now going to add in a new interface requirement between those two components that I've connected together. And just let me get the correct number here. Okay, it's a tie-down interface. We're going to now put in the actual requirement for the tie-down interface. As you can see there, the vehicle shall provide rated connection points that interface with the A400M tie-down arrangements. We'll allocate our priority and do the other metadata as needed. Okay, so this one might be by inspection. Okay, we can complete that. And then the last thing is we need to link this particular requirement to its link, right? So it specifies a particular link, which we know was the actual interface between our infantry fighting vehicle and the A400 aircraft. So we've now created that traceability. So the requirement is specifying this particular interface that we've created. Okay, so that's a very brief trot through how we would use the systems modelling process to create various elements within our system, covering off the operational analysis, the functional analysis, and the design and synthesis. So I hope you can see that these models become quite complex with a lot of information in them. But what I would say is that in doing your systems engineering in models like this, it's very powerful because you actually get to see the whole data set and how everything is connected together. It is far superior to doing your design work in a linear and document-centric fashion. Having done this in both modes now over the years, I certainly wouldn't be doing it in document-centric means anymore these days. Okay, so just a couple of slides to wrap us up, and then we can go back to the floor for questions. Okay, so why would you want to do model-based systems engineering? There's a range of things that I believe are the most important. But for me, the killer issues really are that the modelling provides a single source of truth. So we now don't rely on the actual Word documents or other documents if they're accessing the database. We use the database to provide the source of truth. Anything that's generated out of it looks and accesses the database. It definitely reduces error rates, and for me, you get these patterns, right? So the beauty of it is, particularly from an industry and government point of view, is that when we have these models here, all the information contained within these models, as you can see, basically creates a pattern. And once we've got that pattern, if we then want to create a new design, or if we want to do some what I call middle out engineering, which is system improvements or system elements where we want to add in and improve elements or subsystems within the overall system, we can use these patterns to quickly do our engineering work with basically great productivity improvements, right? So systems engineering using models provides a great fillip, a great way ahead for improving the productivity of our system design process. Okay, that brings us to the end. I hope you've enjoyed the quick trot through. It's a great way to do your system design in models. And yeah, I'd be delighted to take any questions.
Okay, so in the chat we had first question, what tool were you using to do it?
Okay, so that tool is called Capability Architect. It's a proprietary tool, market design developed, sold to the market by a company called System Design Group. It's a good, simple tool. The reason I use it in my training is it's very, very easy and simple to use. It's actually been designed primarily to make it easy to get the data out. So it comes with a nice set of templates that you can use. And it only takes a couple of hours to learn the basic functionality of the tool. So, so I can actually easily use it in my systems engineering and model-based systems engineering classes, and students don't find it difficult to learn how to use the tool. So great tool, thoroughly recommend it. Its strength is not in the detailed design modeling of the physical system, right? So when you get into doing the detailed component design, then you would need to go to an industrial grade tool. This is not the tool for that, but in terms of teaching and in terms of doing what the government does, in terms of generating operational concept documents and P-specs, it is an excellent tool. So Lewis, any other questions?
Yes, so the second one from the chat is, how does this traceability to operational needs apply to private venture R&D projects where products are being developed ahead of operational needs being provided by the customer?
Look, if you're working in a entrepreneurial environment and you're developing things, you clearly must have a view in terms of what you think you are planning to use this particular system for. If you are at TRL1, essentially you are doing test tube related research right at the very start, then that's clearly exploratory, and it's the various early stages of the science process, and you may not know actually what the applications of these things are going to be. You can only dream about them. So I suppose what we're talking about is there would be a point in terms of the TRL system, probably around about TRL 4 and 5, where you would be at a point where you actually know what this thing is that you're supposed to be designing, and you should be able to be thinking about what the operational needs are. Yeah. Because ultimately, everything we design is got to be fit for purpose and designed to meet some user need, unless you are right back at that very, very elementary part of the scientific process.
Okay, thank you. Let's see, next question. Does the tool comply with the unified architecture framework of object management group?
I can't answer that question. For instance, you would have seen what the tool does. Basically, the key features you have seen. It doesn't do elements of SysML, parametric diagrams, and a range of other things like that. It doesn't necessarily use those conventions. So that's one of the limitations of the tool itself. But as I said, for me, and as a teacher of systems engineering and teaching people how to think using models, it's a marvelous tool, and it also does the government stuff really well. So.
Okay, thank you. And let's see. So we do have a recording, and we'll post this on YouTube. Though, Mark, are we allowed to post the PowerPoint also?
Sure, no problems.
Okay, all right, we'll do that. And let's see, what kind of simulation does the MBSC permit us to perform on requirements?
Are we talking about this particular tool in relation to simulation, or are we talking about generally?
Let's see here. I guess Leonardo, do you want to feel free to unmute and expand on that then? He said generally speaking in the chat.
Yeah, look, so the new tools, the high-end industrial grade tools now have well-developed parametric modeling capabilities that interface nicely with tools like MathCAD and MATLAB and things like that. And you can actually do some great simulation and have these running in conjunction and in combination with your systems engineering model. So there's good stuff on YouTube that shows this in action. So yeah, recommend you jump on and have a look at that.
Okay, and now one last question here. Do you perform any requirements coverage analysis either in the tool or otherwise?
Requirements coverage analysis. Could someone expand that question? What
kind of ensure that all your requirements are met? To make sure that everything is covered. There's links and there's no missing links or orphan requirements.
Yeah. So just within this tool, you can go to this particular part of the model here, and you can do a check. So for instance, you can do a check between operational activities and operational needs. Let me see, what have we got here? Operational needs. So the parent is the operational activity, the child is the operational needs, and you can do a check and that'll run up and that will show you if there are any gaps within the actual modeling, that any traces that you've missed. The common ones that you do are, just let me go back, let's have a look here, functions. And then you want to have a look at those with respect to system requirements. That's a very common one. It could be, let's have a look here. Okay, so that's this is a parent to child rather than a child to parent trace. So again, you just run those and you can just see where the gaps are. So yeah, so it does that very nicely and very easily. So.
Okay, I think that is it with the questions, and we have 5 minutes over time, but it was great. Great presentation and questions. So with that, if anyone doesn't have any more questions, Mark, thank you very much. It was a pleasure to have you.
Pleasure talking to everyone today. If you'd like to get in contact with me at any time, just go to the Eggler Institute of Technology website, go to the contact page, just reach out to me through there. Be happy to answer your questions.
All right, thank you very much.
Good on you, Lewis. Thanks, everybody.